Okay, hi everyone. So again, for those who just joined, we're running a bit late, but yeah, we are fine-tuning to the workshop. So it's my pleasure to introduce Katerina, our next speaker. So Katerina Fragkiadaki is an assistant professor at the machine learning department at Carnegie Mellon University. And her research combined common sense reasoning with deep visual motor learning for action perception and language grounding. Katerina got her PhD at University of Pennsylvania, and she was also a postdoctoral fellow at UC Berkeley and Google. And her work has been widely recognized, including but not only with the Best PhD Award and NSF Career Award. So please join me welcoming Katerina, and the floor is yours. Thank you.
Yeah, thank you very much for your invitation and giving me the opportunity to present my work. Do you want me to unmute myself in the Zoom or no? No, do you want me to open my camera or no? Okay. Yeah, so I'm very happy to be right after the Duster author talk because, we're very inspired by this work and mostly we're going to show once we're able to get accurate 3D, what can we do with this? How can accurate 3D help robot manipulation? So that's the first part I will discuss. We see robot foundation manipulation policies, okay, coming out over the time, right? Like every week there is a new VLA model, right, using this fantastic effort, the open source demonstrations of OpenX embodiment dataset and other datasets that are being contributed essentially through behavior cloning, and they try to build this, general instruction following robot manipulators. And many of them follow the following, let's say, architecture. There are a bunch of images coming in that are being encoded with some pre-trained feature backbone, and they're used to denoise essentially trajectories of the grippers and effector. Okay, so often we use diffusion objectives because that was one of the biggest, in fact, revolutions in behavior cloning. The fact that instead of using regression or VAEs, we have better generative models, super instrumental to handle multimodality in demonstrations. Recently, like about a year ago, we have presented the 3D analog of this architecture, okay, where you have your noise pose estimates, what you see here on the bottom, and instead of building 2D feature maps and using 2D feature maps to denoise those trajectories, you use 3D feature representations. And so I'll show you what are the benefits of that, why this is important. And of course, the details matter here of the execution. So the main idea of our, what we call 3D diffuser actor, because that combines ideas of 3D and diffusion. The main idea is that action tokens and visual tokens live in the same 3D space. So here's how it works. You have your robot that can watch the scene from an RGBD camera, and you take the RGB image, you featureize it, you get a 2D feature map, and every token has a depth. And you can use this depth to unproject those tokens in 3D. And if you have other viewpoints, you can just aggregate those feature tokens. So you have a larger feature cloud. And the idea is that if you have multiple views, those better be calibrated so you know the relative camera pose between those. And then you're going to use this 3D feature cloud to denoise robot trajectories. And specifically, robot trajectories here are essentially gripper orientation and translations on the 3D task space. And so we have two types of tokens here in our denoising transformer. There are the visual tokens, which are exactly those patch features with XYZ coordinates, and we have those action tokens, each one of which will decode essentially a pose for the robot's end effector in the future. And the important idea is that those have positional encodings in the same 3D space. So essentially, we represent the visual tokens in the robot gripper's coordinate space, okay? They need to be in the same space. And because they're in the same space, and we want our model, our 3D denoising transformer to be translation invariant, we're going to use relative attentions. And relative attentions essentially look like that. Only the difference between the positional encodings of two tokens influence their attention, not the absolute coordinates, because where you set the center of your coordinate frame is absolutely arbitrary, and you don't want your manipulation policy to remember about that. So we have this 3D denoising transformer that essentially, also takes, of course, the language instruction because we're going to be, training multitask manipulation policies. So this is the language instruction. These are the visual tokens, the 3D visual tokens that I described. This is a proprioception of history of proprioception for the robot to know where this robot gripper is. And here are these noise trajectory tokens that are going to decode the trajectory of the robot. Okay, and it's important this trajectory to be in task space as opposed to body joints, because body joints are not in the same space as the 3D visual tokens, right? So this is important. So then once you train by taking essentially trajectories, adding noise to them, and then asking the denoising transformer to predict the noise, at test time you denoise sequentially, and you go from random noise into a predicted trajectory of the end effector. So here I'm showing 60 samples of that model. I'm only visualizing the translation just for you guys to see. They concentrate around the basic modes of where this gripper is going to go next. Okay, this is just for visualization purposes. And here, this model can be used to predict continuous trajectories or discrete key poses. And in the second case, you need to use a motion planner to go from one predicted key pose to the next. So here I'm showing 3 key poses. You see, again, we have 60 samples, but they are all concentrated around 3 modes, because at training time, when we collected those demonstrations, sometimes we would pick up the green grape, sometimes the red one, and sometimes the black one. Okay, so you see that our generative model can exactly capture the relevant modes, not drop modes, and not hallucinate new modes. 3D diffuser actor has a very good performance in 2 very different benchmarks, RL bench, which is designed mostly for 3D policies, and Kelvin, that is designed, mostly 2D policies are evaluated. So this shows how general it is, and it has been used by many, other labs. And recently we have extended this to bimanual manipulation. So now you have 2 hands and 2 grippers, and the idea is going to be exactly the same. We're going to also switch from diffusion to flow matching so that we have much faster inference with much fewer number of denoising steps. But the idea is the same. Again, you have a set of 3D visual tokens, and now you have 2 sets of action tokens, one for the left gripper and one for the right gripper, and you have your language conditioning, and then you do iterative denoising, and the denoising looks like that, essentially. So you see the blue. Yeah, so the blue and the green are the 2 grippers, essentially the 2 arms, and you see how fast with only 4 denoising steps we're able to do the inference in that 3D space. You see this is not a point cloud, this is a feature cloud, but I'm showing a color point cloud for visualization purposes. Okay. So our baselines here are going to be pi0, PERAC2, diffusion policy, 3D diffusion policy, ACT, and any bimanual. Pi0 is a well-known generalist policy that is a 2D. Again, it has a flow matching action decoder. And 3D diffusion policy, interestingly, is very similar name-wise to our policy, but they don't have this core idea of having action tokens and visual tokens on the same space. And in fact, we evaluated 3D diffusion policy here on Kelvin, and it had the lowest performance. You see this blue, little bar, because they just take the point cloud and encode it and attend to it with a point to decode, to denoise the trajectory. So I just want to mention here that 3D policies doesn't mean that instead of taking the image, instead I'm going to look at the point cloud. I think it mostly means how do you reason in 3D space directly during denoising. So every denoising step looks at the 3D tokens in that 3D space and predicts where it needs to go, where the gripper should go. So we adapted, so we wanted to test those baselines in the PERAC2 bimanual benchmark, and we adapted pi0 to predict key poses, because all the other baselines predicted key poses, and this increased its performance. So the results look as follows. On average, 3D flow actor does much, much better than the baselines. You see the average across tasks here, and then I'm showing the performance on some tasks. We made the exact analog of a 2D flow actor. Sorry, I call it diffuser, but it's actually flow actor. Sorry about this. and it's the green. So there is a drop if you reason in 2D. Okay, so the action is here, and the 2D visual tokens are in a different 2D space, and the 3D tokens are in the task space, and there is no essentially, in the positional encodings, there is nothing to connect them directly, okay? So you have a direct drop in performance. Now, another big question is how important is to have multiple cameras, which is completely unrealistic. If you have a robot moving around, you are not going to have 3, 4 cameras looking at the scene, and there is not a big drop in performance if you use one camera versus using, wrist cameras and external cameras and so on. So the 3D reasoning is the key idea here, as opposed to having multi-view input. Yeah, in comparison to a 3D diffuser actor code, I mean, our 3D full actor, which soon is going to be released, is going to be much, much faster, much, much easier to train. And yeah, we hope that you guys are going to take a look and you'll find it useful. Now, what about the real world? Why 3D policies have not gone in the real world? So we wanted to do that. So what we got is we got a mobile Aloha with this excellent of a cheap platform that you can very easily collect kinesthetic demonstrations. And we collected 40 demonstrations for each one of those tasks, okay? And again, we're going to predict the end effector trajectories in the task space, same as before. And so, it did reasonably well. So we designed tasks that, both arms are necessary here with ropes and so on and so forth. And we just wanted to figure out what are the challenges of moving these 3D policies from simulation benchmarks to the real world. And I'll tell you what the challenge is. The challenge is the calibration. So calibration means that the robot needs to know where its gripper is in the camera frame, okay? Or it needs to know where the visual token is in its gripper frame. One or the other. So that action tokens, which is the gripper, and visual tokens, which is the scene, right? The RGBD image can be put in the same space for 3D reasoning. And we know calibration, maybe in expensive robots is possible. For this mobile Aloha, it was actually challenging, especially when the gripper is extended. We had 1 to 2 centimeters error on the calibration, no matter what we did. So yeah, in real world, again, 3D diffuser actor is has much better performance and has much faster inference and much fewer parameters than the alternatives, which is 3D policy and Pi 0 here. We were managed to fine tune on the same training data. I can show you, many failure modes. But I think the important thing to highlight is the calibration problem, right? So you think your gripper is somewhere in the camera frame, but guess what? The gripper is somewhere else. And all the data sets that come out, Bridge and Droid and RoboMind and the IAGBot benchmark, that none of them is calibrated, right? None of them is calibrated. So we can use essentially the robot location in the camera frame, either 2D or 3D. I mean, we're using 3D, but you can also use in the 2D, where the gripper is in the image, essentially. This is what I mean, camera frame. So essentially, we put some effort here on camera calibration to fix that one using machine learning. So what we did is we started with this excellent paper from Coral 24, differentiable robot rendering, where we trained a neural network to map body joints to 3D Gaussians of the robot. I mean, you need to tell me the robot, I'll take the URDF of that robot, I'll go in simulation, render it in different poses and from different views, and then I can train that neural network, right? Through rendering losses. Essentially, the neural network predicts 3D Gaussian parameters, you render Gaussians differentiably, you compute the rendering losses, and you backpropagate to the weights of doctor robot. So once you train that model, what you can do is you can go in the real world now, you have a particular video in Droid or Bridge and so on, and your goal is to infer the rotation and translation of the camera in the robot's coordinate frame, okay? So you need to figure out where is the camera taking picture of the robot. Do you see? So, and each time you take a picture, essentially you render those 3D Gaussians for that view, and then you match the RGB, the flow, the point trajectories, and then you can optimize now that transformation holding doctor-robot neural network frozen. And in this way, we're able to calibrate a lot of videos, okay? Now, having said that, I want to mention that the body joint parameters, like what you see here, the P vector, is known because these are all videos of demonstrations, essentially kinesthetic demonstrations from Droid or from Bridge and so on, where the body joints of the robot are annotated. Okay, that's how policies are trained, to take images as input and predict body joint trajectories. So these body joints are known. What is not known is the camera placement, okay? So in any case, now our goal is to use this calibration, let's say machinery, to go and calibrate all the data out there and be able to train 3D robot policies with lots and lots of data. Yeah, so this is what happens in the real world. But the thing is, no matter how much time we spend, we cannot really, I mean, it's not scalable to expect humans and robots to really scale up demonstration trajectories. I mean, let alone that, to be honest, I personally really don't like learning from demonstration trajectories. I mean, it's very biologically implausible. Very few times our parents took our hand and really moved it to do something, or our dance teacher moved our legs on something. And this is like, mostly humans learn by watching other people as opposed to being, teleoperated. Yeah, so the question is, what can we do instead of behavioral cloning? So can we use now 3D, not implicitly, not as a feature representation, but as explicit 3D, to scale up data in simulation? Can we replicate the real world in the simulation? And there is this big, let's say, distinction between manipulation and locomotion. In manipulation, the best demos come from policies trained with behavioral cloning, here by 0, while in locomotion, the best demos come from sim to real. Reinforcement learning is simulation and sim to real transfer, right? Huge difference here between the two fields. And there is a good reason for that. For locomotion, this robot here is going to go down the hill. There's no hills in simulation. It was just a rigid scene, right? You don't care to represent the world very accurately. While for manipulation, you really need to be super accurate of where the objects are, what's going to happen to the objects if I move them, and so on. So the question is, can we do in manipulation what people did for locomotion, really scale up the data in simulation? Okay, because we cannot afford essentially teleoperation and behavioral cloning. So one thing that we did here, Zianzhu led a big multi-university effort on building a more general physics engine. And now you say we already have a lot of physics engines. The big idea behind our recent physics engines here we call Genesis, and Chuang may talk more about this later, is how to make it easy to use, how to make it general, really be able to handle lots and lots of different materials, rigid, liquid, gas, deformable, thin shell objects, granular objects, with all the different solvers, coded from scratch in Tai Chi, in GPU parallelizable programming language, with very good performance, thanks to very good coding of the parallelization, especially in piecewise rigid scenes, rendering, and so on and so forth. And you see here the same scene can be taken care by different physics solvers depending on the type of the material. All right. So we have a physics engine now, we have the platform, and the question is, what do we do with it? How can we automatically populate it with scenes and assets and tasks and reward functions to train robots? Because if you have humans coding all these things up, then you're not going to save time. Like what we're trying to do to take the human out of the loop, you won't be able to do it unless you can also automate the data collection in simulation. So we have started an effort on automating everything in that pipeline, from generating of the assets to texturing them to assembling on a scene, designing a task and reward, and of course not only us but multiple people in the field. And for me, a lot of pieces of this pipeline are super exciting. For example, computer vision is very close to 3D-ifying any image or video right now. So there was this big revolution in 2023 with Dream Fusion, where you can take any single image, and make a corresponding 3D, neural field or mesh and so on with score distillation sampling. And by using exactly that machinery, we're able to create tons of assets for the scenes we cared about, like food, for example, with carrots, pieces of carrots, beans, and so on and so forth. And then once you make the geometry, then you ask the language model, okay, how big shall I make it, and what physics properties I should put? And the language model knows very well how the carrot should feel, and how the fact that a pumpkin is bigger than a cauliflower, etc., and predicts very plausible physics quantities. And we're not trying to make here twins. We're trying to make distributions, plausible distributions in the simulation that can, encompass the real world. We're not trying to find these golden, physics properties of the cauliflower. We just want something plausible here. And look at these two excellent papers, Huang 1, 3D 2.0, and others 2.5. And the CAST paper that takes a scene and makes a bunch of 3D meshes. I mean, this is absolutely wonderful to see. You have the picture of the shoe, and not even scroll distillation sampling. When I told to you about SDS, that was an optimization process. Now there is no optimization. These are feed-forward networks that take images and spit out, sign distance functions that can be mapped to meshes directly, thanks to very, very, very big data sets like Objaverse with tens of millions of assets, where you can learn that mapping from image to mesh. Okay, and so you can use this for your assets. Absolutely, we're not there. There's no way you can learn to tie the shoes with this rigid shoe here. I mean, the laces here are rigidly attached on the shoe. But we totally see a future where agentic systems are going to be looking at images and thinking about, how to build a mesh, where to put the holes on the shoe, how to make the lace, how to pass the lace in the shoe, and so on and so forth. So this is one, line of research that I'm very excited about. And let me quickly talk to you about our tiny contribution here, led by Yuchen Lin on PartCrafter, of how to map images not to one mesh, but rather to a set of meshes for the different parts of an object or the different parts in a scene. So Huang 1 3D, as well as other models, have revolutionized the image to 3D with super large scale models of latent diffusion that take 3D point clouds to a latent space, okay? And then they train diffusion process in that latent space. So there is a VAE, so let me show you the VAE here, that takes surface points, what you see here in the upper right, surface points on the point cloud, it encodes those into latent vectors, okay? And then decode sign distance functions, and from sign distance functions you can build a mesh, okay? Through marching cubes. So we have built those VAEs, and what this TriPoSG does, essentially trains a diffusion model on that latent space with an incredible amount of data. There are 4 billion parameter model, really, really large scale to map images, image prompts to essentially, to denoise essentially, to denoise essentially the latent 3D point cloud features. And then once you denoise the tokens, the decoder of the VAE essentially will map them into a sign distance function and you get the mesh. So this happens in a monolithic object, but can we go to part-based? Can we go in a part-based? And what we did is the following. We saw that in Objaverse, there are annotations for parts that people throw away. And then we said, what if we use those annotations? And what if we make a compositional latent space? Instead of just having one set of latents for the whole object, we have multiple sets of latents where each set of latents takes care of one part. So the purple set of latents take care of the purple part, and the orange set of latents take care of the orange part. And then we replicate the VAE across the parts, right? And we're not even fine-tuning the VAE. The VAE that was trained for objects can work really well for parts as well. And now in that latent diffusion, instead of denoising the latents of one object, we denoise jointly the latents of all the parts by alternating between self-attention within part and cross-attention across parts. So essentially, and we start with all the weights of the TriPoSG model. So this is huge because they trained on millions of training samples and we trained only on 50,000. So the pre-training is absolutely critical, and how you repurpose the architecture to go from denoising one single object to denoising parts. And of course, the image prompt is also injected into that denoising process through cross-attentions. So things look like this. There is an image, and jointly all the parts are being denoised, as you see here. And you can vary the number of parts that you can ask for. And why I find this super exciting is because all previous models, if they wanted to denoise multiple things in an image, they had to first segment the part. So they segment the part, and then you feed this as a segmentation prompt to your denoising latent mesh. But the problem is, if you have an object, many parts are not going to be even visible in the image. So if you have a car, you're not going to even see the parts. And here you see the bed is very, for example, occluded. Now, this is in the scene level. Now, if you go to an object level, things are even worse. Here, for example, you don't even see the parts. So this segmentation prompted methods could not actually even be used. We have as a baseline this hollow part that first makes a whole mesh and then segments that mesh and so on. And our model just does the whole thing immediately at one shot. So you see, we have an image, we predict batch of parts by cross attention to the image. I think this is very cute. Like we use the image as a prompt into that 3D generation process. Okay, not like as a very strong guidance, like, oh, using pixel aligned Gaussians and so on, because so many things are missing from the image, right? So many things in the scene are just not there. Okay, so now what about target? So we have assets and we have physics from, the LLMs. And then now we need to set tasks and reward functions and so on. And how we're going to do that? We're going to translate videos to simulations. We can take a whole video and make a corresponding simulation by making a real-to-sim pipeline of, detecting the objects and segmenting them and 3D reconstructing them with the machinery that I just told you. And this is precisely what we did in this work Robot Arena, which we're going to present on the 25th, on a workshop in the 25th. And the purpose of Robot Arena is to automate evaluation of robot manipulation policies in simulation. Okay, really, really, really scale up the evaluation environments and tasks by translating automatically without any human involvement a video to a corresponding simulation evaluation environment. Okay, so what happens essentially is you take the video, you make a corresponding simulation environment by segmenting the objects and 3D reconstructing them, place them in the right place, as well as you create perturbations on that simulation environment, and then you automate even the scoring and evaluation using visual language models and some techniques we'll discuss, in a few days if you want to join that workshop. Great, and this brings us to the main topic, which is world models. How many minutes I have? 5. 2, 3, okay, not that much. Okay, so world models, maybe I want to very quickly to say that world models, we have video generative models that generate the future of the scene in pixel space, okay? And all the time they hallucinate, and also they are very slow. That's the other problem. Although, I truly, truly love them, and, I think the revolution are going to come soon from that direction. But if we look at game engines, they can also generate beautiful videos, but they don't generate pixels directly. What they do is they have entities and they just move them around, and they also move the camera around, and then they render. So they predict in this much structured space. So motion is very important, right? And there is explicitly this constraint of permanence of entities over time. So the question is, can we also do the same thing? Can we predict in this structured way? That was the topic of the workshop, structured world models. So the structure is essentially the motion, the 3D scene and motion. That's one way to understand the structure. That's one way. I'm sure there are multiple ways. So point trajectories are robot subgoals. There has been many, many recent papers that use point tracks in a video to represent goals for robot policies. Not just tasks, but rather fine-grained motion tracks. And I want to mention that this work of point trajectory started with my student here, Adam Harley, from his work PIPS, where it was the first work that says don't chain optical flow fields over time, rather than take multiple frames together and predicts trajectories directly through an iterative refinement process. And recently we have a paper here led by Adam Alltracker that really pushes again, PIPS is his first paper that started this multi-frame trajectory, and Alltracker has the fastest and most high quality point tracks for you guys to use. If as sub-goals on your policies, you see here every point on the video is tracked in different resolutions. And also we have a recent work with 3D point trajectories where the tracking happens directly in 3D in a persistent space where camera pose is taken into account, and camera pose comes from Duster or some other fantastic, 3D extraction ideas from videos. And this is the very, very last part of the talk, neural simulators. So can we, much like a physics engine, instead of using Newton's, Newton's solver to find the solution to these equations of motion, can we instead learn those equations of motion? Can we build neural models that condition on initial configuration of a point cloud and then action of the robot predict where the points are going to go? And you see, you generate a video, you move the points around, you color them, and you render, and you have a video. And we'll have 2 versions of this. The version 1 is you condition on the actions, and the version 2 is you don't condition on the actions, you actually predict the joint action and object motion trajectory distribution. So we predict the distribution of both actions and objects. And we have this architecture that very much is borrowed from video generation models, where instead of predicting pixels, it actually predicts motion trajectories, and it's a diffusion model. You take motion trajectories, you add noise, you predict back the noise, and because there are too many points on your point cloud, essentially you have this set of latents, much like a perceiver. For those that know the paper, set of latents here, and the attentions are between the point features and latents. And you created, how do you learn that point trajectory? It's very difficult to get 3D point ground truth from videos, so you can collect them from simulators. And then, you can test how well this model does. And, it does pretty well. And it does much better than graph neural networks that used to be deterministic. There are many, many papers that try to predict 3D trajectories of particles with graph neural networks. But because we have a generative approach, we're able to do very well for long-term prediction. And we fire this object essentially recurrently over time. And this is the last kind of, unfortunately, we don't have that many results to back this up, but this is what I'm most excited about, is that when you model both the distribution over motion of your object particles and actions, then you can do more predictive control, not with the classical way and by searching over action trajectories and so on and optimization, but rather through guiding that diffusion model. You can set states and goal states in your object, and through guidance infer the actions that will get you there. Because this is the standard thing that do for model-based reinforcement learning and has not worked so far. The action optimization essentially will exploit mistakes of your dynamics model. So what if we see this completely differently? Let's build trajectory generative models and guide them. And this is the way to infer the actions that achieve corresponding goals through essentially differentiable constraints and rewards. And this is something that we're the first to try this out by encoding the state as object particles and so on. So the takeaways as 3D reasoning for robot manipulation. Computer vision is taking care of bringing us from images and videos to simulated scenes, and generative models over 3D particles will try to bring the essentially machine learning analog of physics engines. And thank you very much for your attention.
Thank you, Katerina, for the great talk. I think that in the interest of time, while our next speaker sets up, we can get one quick question. Okay. Let me get there.
Yeah, great work. One question, in all your examples, when you do manipulation, the action doesn't change the world in any significant way. But in the real world, when we do actions, we pull an object, something else falls down, right? So how do you incorporate dynamic changes in the world in your approach?
Yes, so I talked about many approaches. So about the 3D robot manipulation policies, I want to mention that at every time step you take as input the image. So essentially it's a closed loop policy. Like each time you act, the scene changes, you take as input the new scene, and then automatically you adapt. Okay, so it's not that you predict a long trajectory and then you close your eyes. No, even if you predict a long trajectory, you only execute the first action and predict again. For the last part, again, you take into account the world because you model essentially the object trajectories, and the idea is the same. You infer the actions, you execute the first, and again, you guide again and plan again. So it's a closed loop system. But thank you for your question.